Next part in our lecture is the index properties of soil. It is one of the best, or the most important properties of soil is the index properties, especially for clayey soil. This is very important. So if I'm speaking about clay soil, then water content is very important, because clay properties depend on the soil. So this is just a description of the test procedure. You just read it to understand it. But if I want to study the water, to know the water content of a sample, then I just have the sample, weight it with the water, and then put it in oven, and so that all the water go outside, and then weight it again, and then compare, and so on. So it's just a normal procedure. It is given here. You don't have to memorize it. I'm not going to ask you, and nobody is going to ask you to memorize how to do a water content test. But you can read it in any place and do it yourself if you need to do it in any time. There is something called specific gravity. We just studied the water content as an equation. We studied the specific gravity, but how to do the tests in the lab. This is the equation of the specific gravity, and this is the definition of all the weights that will be used in our design. You just substitute by measure the weights, substitute in the equation to get the GS of the specific gravity of the soil. Let's here study what are the types of soil. We have these two types of soil. It's either fine-grained soil, cohesive, or coarse-grained soil that are cohesionless. Do you know what is an example of cohesive and cohesionless soil? Do you remember? Cohesive, like clay. Cohesionless, like sand. Cohesionless, it means that particles do not stick together. Sand. If you have some sand in your hand and put it like this, you'll find sand running between your fingers. So it is cohesionless. But if you have a piece of clay in your hand, it will stay in your hand as one piece. So it is cohesive. Samples want to catch each other. So these are the two major groups. Usually in fine-grained, which is like the clay, we have always the problem of water. Increasing the quantity, decreasing the quantity, and so on. But in coarse-grained soil like sand, always the proper sand is not. You don't have any problem with water. If you have sand and you put some water, or you don't put water, it's the same. But the problem is always in compaction, الدمج. So in sand, you always you want to focus on void ratio. In clay, you always focus on water content. These are the major, the more important things. So in soil consistency, it's a fine-grained, for fine-grained soil, of course. This is just to remember what we have said about the three-phase diagram and how we increase the quantity of water or decrease the quantity of water. What is a dry soil and what is a fully saturated soil, and so on. Just to remember. But I just want to go to this curve. this curve, it's written in Arabic and in English at the same time. This is very important because it gives you definitions of three main, very important properties. We call this section is called index properties. These are the index properties, or what we call it Atterberg limits. Atterberg limits or index properties. These are very important properties to define the clay or the cohesive soil. Something called shrinkage limit, something called plastic limit, and something called liquid limit. In shrinkage limit, let's start before the shrinkage limit. I have a sample of clay that is very, very dry with no water. I start to pour water. When I pour water on this sample, the volume of the water of the sample starts to increase because water comes inside the clay. So the total volume increase. So you add water and the volume increase. Add water and the volume increase. So if I follow this graph, so here is the water content. As I increase the water content, the degree of saturation increases. It means that increases till it reaches 1. It means that I am filling all first I'm filling the voids, because in any dry clay sample, or dry sample as in general, I have voids. So if I start pouring water, water will go into the void. So when water goes inside the void, then the volume is not going to increase because the void is inside. So at the beginning, I don't have change in volume. I'm just adding water to fill the voids. Till I reach a degree of saturation of 1, it means that all the voids are full of water. Then whenever I add more water, what will happen? The degree of saturation will not increase because it is still fully saturated, but the total volume will increase. The whole sample will expand. So this is what will happen. Here, the degree of saturation is increasing till the shrinkage limit and continues straight line. But what about the volume? The volume at the beginning, it does not increase because I'm just filling the voids till I reach the shrinkage limit. Once I reach the shrinkage limit, the total volume starts to increase. So it's going up till I reach here. I first reach something called plastic limit, or in Arabic it's called حد اللدونة. The other one, shrinkage limit, was حد الانكماش. And if I increase more, I reach liquid limit, which is called حد السيولة. So I have now here 3 limits. I need to define them. How can I find them in a lab? So these 3 limits are called Atterberg limit, named after the person who proposed them. First, this is the shrinkage limit. This is the description that we have just said, and this is the plastic limit, and this is the liquid limit. How to do this in lab? There are standard tests in lab. One of the tests, this is a test to determine the liquid limit. You take the sample, you put it in a bowl, and you make just a scratch in this sample, and then you start with a device that shakes this sample. After many, by blowing it, you just blow the sample with something, and you count the number of blows. If you need a fixed number of blows to make this, here you scratch the sample, so you can see the bottom of the of your bowl. If the two sides collapse together in say half an inch, as the experiments say, then the number of blows that makes you reach this is the shrinkage, is the liquid limit, and so on. Every test have a special procedure that you can find in lab. So this is the procedure for the liquid limit, and this is a written procedure of it. The plastic limit is a little bit different, and it is easier. The plastic limit, you can do it on site. They tell you it's called the threading experiment. You just take the clay, put it in your hand, and make it like this, as if like this here, trying to make a thread. If you manage to make a thread that is 3 millimeter in diameter, then this is the plastic limit. So they just give you a number so that we can all define a sample if it is in the plastic limit or more than the plastic limit or less than the plastic limit. So this is another experiment for the plastic limit. Then I have here something called the plasticity index. Plasticity index is the liquid limit as a value minus the plasticity, minus the plastic limit. So liquid limit minus plastic limit, it gives you something called plasticity index. Plasticity index is a soil property that is very important in, if I come to define what material to be used in compaction, they tell me that plasticity index should not be more than a fixed number, and so on. So it is an important number that we are going to use later in our engineering work. Another thing called relative consistency, and this is the equation of the relative consistency. And there is a table, and this table of course is given in the code, that gives you if I have soil with relative consistency from say 0 to 0.25, it means that this soil is very soft. So now here you find that I'm trying to change everything in our life. Instead of being depending on my judgment into numbers. If I give you a sample of clay, you tell me that this clay is soft, and I give it to somebody else, you will tell me it is very soft. How can I know who is correct? They tell me that to be very soft, then the value of CR, which is the relative consistency, should be between 0 and 0.25. So now we have something to, if I disagree with you on defining is it soft or very soft, then we make an experiment. If the number is less than 0.25, then it is very soft. More than 0.25, then it is only soft, and so on. So we are trying to change everything that is subjective into things that are definite, numbers. Liquid limit, and PL is the plastic limit. Maybe it's not written here, I have to check. Yes, it is liquid limit, LL, and maybe, and here liquid, LL is liquid limit. Another example, using the new equations that we have just taken, depending on the liquid limit and the plastic limit. You have a sample, you have a water content, plastic limit, liquid limit, and so on. Determine the plasticity index, the relative consistency, and so on. Just normal substitution in the equations to get the value. There is something called activity index. The activity index is very important for some type of clay, because if I have active clay, it means that this clay is active. It wants water to go inside it and to increase in volume. Then it will make problems for me if it is below my foundation. If I have clay below my foundation and it is very active clay, then this clay will make problems for me. So they try also here to define this activity. If AI, which is the activity index of this soil, of this clay, is less than 0.75, then it is not active. It is between 0.75 and 1.4, then it is normal. More than that, it is active. So this is another soil property that is very important in our the use of clay material in any project, because it affects the swelling of the clay. It is important in something called problematic soils. We have in clay one type of clay called expansive clay. This is very this makes lots of problems. So if I manage to calculate the activity index of the clay, then I can say it is active or not active, and I can use it without problems. Relative density. The relative density, this is the equation of the relative density related to the E. This is important because I will just give you a problem that will help you to understand how can we use it in our engineering life. For relative density, you have these ranges to describe the soil. If it is less than 15, then it is very loose, and more than that, loose, medium dense, dense, and so on. So it is relative density related to compaction of soil, because here we said that the relative density is related to E. E is void ratio. We said that sand is affected by void ratio, and clay is affected by water content. So if I have a property that depends on E, so it mainly is related to sand and sandy soil. So it gives me the description of the sand. Is it compacted enough or not? If I have a relative density of 85 or more, then this soil is very compacted. It is good. But if I have 15, 35, 50, this is not compacted, and it needs more compaction before I put my building on top of it. Relation between this is another equation relating two cases of the sample. If I have two samples, one compacted and one not compacted, what is the relation between V and E? They said that V1 divided by V2 equals 1 plus E1 divided by 1 plus E2. Of course, if I say V1 and E1, it means that the E that is corresponding to the same V, E1 and V1 for one sample, E2 and V2 for another sample. So if I need to get a relation between two samples, then I can use this equation to relate volume and void ratio. An example. This example is a little bit important because it helps you to understand why we are studying these equations. In one site, they have three quarries. Of course, if you need to get sand to use it in your site, then you have to buy it from another place, from outside. So you go outside, you go to many places, you find that one of them is telling you, I can give you the 1 meter cube with 13 pounds, the other 16, the other 22. Which is better? Usually we may say that the one with the 13 is okay, but maybe the one with the 13, the sand that he has now is not compacted on his site. So the 13 pounds for 1 meter cube of the soil on site contains amount of material that is less than another place where the price may be 16, but it is very compacted. So I have to study this. So I have 3 cases. Natural void ratio, which is the void ratio in place. On site, it has this void ratio. There is something called the maximum void ratio. Maximum void ratio is the void ratio when you compact the sample to the maximum. It cannot be compacted more than that. Minimum void ratio, when you leave it loose. If I bring sand from the soil and I just put it in a bucket and just throw it on the ground, it's not compacted. So this is the minimum. I mixed. The minimum void ratio, it means the most compacted. The maximum void ratio, it means it is not compacted at all. Okay? So now I have these 3 numbers and I have the price. So before I compare the price, I have to compare the amount that I will need. So if I use these, just follow this. You have to read it first before I just go through it step by step. But I use the first equation because in this they tell me that I have to fill a gap. I have a hole in the ground. I want to fill it. This hole is 36,000 meter cube. So I need to bring sand. I bring it either from place A or B or C. And I have the prices and I have the properties of it. Which is better? So first of all, and they said that in my site I need to compact the sand to be 85% relative density. It means that I need to compact it 85%. So using the 85%, I will get the E natural of the soil that I will need. I use this E natural and use the other equation to get the amount, the volume that I need to bring from the first place. So from the first place, which is A, I will not going to tell him, give me 36,000 meter cube. I will tell him, bring me 41,684 meter cube. This is the amount that will be enough to reach the 85% compaction. So from the first place, I will need this amount. From the second place, I will need this amount. From the third place, I will need this amount. So it is different. So for each place, I take the amount of volume that I will buy, multiply it by the price of the meter cube to get the amount that I'm going to pay to this person to get the 85% compaction on my site. By coincidence, in this problem, soil A is the most economic, but I can just manipulate the numbers to give you a case where the soil A, which is the one with the less price, is not the most economic. Maybe the other one is economic. Maybe if I come in the test, I may use another thing to show you that not in all cases the unit price that the people give you is the minimum. It is like if you go to a shop to buy something. I will tell you that I go to buy apples, and I have here a basket full of apples, this another basket full of apple, and another basket full of apple. And then I ask, how much is this basket? One tell me that this is for 20, 30, 40 pounds. So of course 20 pounds is the cheapest. But if this 20 pounds includes 4 pieces of apples or 4 apples, and the other one, which is more expensive, but it includes 7 or 8 apples, so you have to judge which is more economic for you to buy. So this is an example. So I just put this example to try and show you that it is not just equations. It's equations that are transferred into mathematical things that we can apply in our daily activities in engineering. This ends the second section of this lecture.